Let's talk about the nuclear reactions that include the bombardment of neutrons and protons. All right, just to refresh your memory, because it's been a little while, induced radioactivity is where we have a stable nuclide or stable nucleus of an atom that absorbs nuclear particles. It becomes transformed into a radionuclide through a nuclear reaction. This occurs both naturally in the atmosphere or deliberately in the lab. So let's start with neutron bombardment. General reaction for neutron bombardment, we start with an element, we bombard it with a neutron, that's why it's on the reactant side, and our mass number is going to increase by 1, which makes sense because we're adding a neutron, and our atomic number does not change because we didn't add a proton, we added a neutron. So we're able to find our species will stay the same, but the neutron number and the mass will change by 1. All right, a natural example we have is we are able to, or not we didn't do anything. Cosmic ray showers produce neutrons, and these are absorbed by atmospheric nitrogen-14. So this is a little bit more complex example than I really wanted to show you, but I'm going to show it to you with a caveat that here we can see that there are two products. I will tell you if there is that second product and what it is so that you can account for that. But let's work this as if you had already known that from the beginning. So we have our atmospheric nitrogen-14, 7 protons, that's a bad color. We have 7 protons, 14 minus 7 tells us we have 7 neutrons for a mass of 14 on the nitrogen. Our neutron has no protons, has 1 neutron, and an overall mass of 1. So our mass for the reactant side is 15. Looking at our product side, carbon-14 has 6 protons. 14 minus 6 tells us we have 8 neutrons for a total mass on carbon of 14. In this particular bombardment, we're also producing a proton or a hydrogen. So hydrogen has 1 proton, no neutrons, for an overall mass of hydrogen of 1. Wonderful, this adds up. We've accounted for all of the neutrons and protons in this species. Again, I will tell you if there is a second species that's created by the bombardment, and I'll tell you what it is. All right, if we are going to deliberately bombard by neutrons in the lab, let's use cobalt-60 for an example of this. So cobalt-60 is produced in a nuclear medicine lab by exposing a normal or a stable cobalt to neutron radiation from a nuclear reaction. This makes the most sense. You don't want to just store cobalt-60 because it's going to constantly decay. So the ability to produce this on demand is wonderful. So cobalt-60 is our product. Okay, we're going to start with cobalt-59, which is a stable isotope of cobalt. We bombard it with a neutron, forming our cobalt-60. So cobalt has 27 protons. 59 minus 27 is 32, giving us a mass on cobalt of 59. Accounting for the neutron that we had, no protons, 1 neutron, total mass of the neutrons 160 is our mass on the reactant side. Let's take a look at our product side. We have 27 protons because it's still cobalt. Now we have an additional neutron. 60 minus 27 is 33, but again, the value is the same. We have the same amount, the same mass from the reactants to the products. All right, let's talk about proton bombardment. We use this in particle accelerators to split atoms. So it's going to require a massive input of energy. We did use this attempt to try to generate energy as an energy source, but the technique has since been replaced by neutron bombardment. So the symbols for bombardment by a proton are the hydrogen ion, which has no neutrons, so it really represents a proton, or we can just talk about a proton. The general reaction, we start with an element, we add a proton or we bombard a proton. And because we're adding a proton, your atomic number increases by 1, and therefore your mass also increases by 1 because you are absorbing that proton into that element. Here's our sample reaction. Argon-40 is bombarded by a proton and it forms a new nuclide and a neutron. This is a good example of when I tell you if another species is formed, what that species is. This is a much more fair question to ask of you. All right, so we start with argon-40. We bombard it with a proton and we're told it forms a neutron and some new species, which you would have to be able to find, but we've written this out for you. Looking at our reactants versus our products, argon has 18 protons. 40 minus 18 is 22 neutrons for a total mass of 40. My proton has 1 proton, no neutrons, but a total mass of 1. So 41 is the overall mass on the reactant side. Doing a similar accounting for our product side, we form a neutron, no protons, 1 neutron, total mass of 1. And our new species is potassium. Remember that we're going to add 1 to the atomic number, so we go from 18 to 19. And typically we would add 1 to the mass as well, going from 40 to 41. But because we have a neutron, that accounts for why the number is still at 40. That neutron carries the mass of 1. But when you add these up together, you still have 41, showing that we have accounted for all the neutrons, the mass, and the protons. Oh man, I'm hitting you hard with this first example, but let's see if we can get through this together. We are to write the balanced nuclear equation for the bombardment of nickel-58 by a proton, which produces a radioactive isotope and an alpha particle. Great. Okay, so let's start out with what we know. We know we have nickel-58, that's the mass number. The atomic number is 28, just looking on the periodic table. We know that it's bombarded by a proton. We know that it produces an alpha particle and some other isotope. So I'm going to leave that blank for just a quick moment while we think through this. When we're bombarded by a proton, my mass goes up by 1, so 58 goes to 59, and my atomic number goes up by 1. 28 turns to 29. So this should be the species. Whatever atomic number 29 is, that's a species I should form. But I'm told that I also form an alpha particle. So instead of having a species with atomic number 29, I have to account for the 2 protons in the alpha particle. So I'm actually going to produce something with the atomic number 27, which is cobalt. And instead of having a mass of 59, I have to remove the 2 protons and 2 neutrons that the alpha particle has from this new number. So I actually have a value of 55 for the new mass. Now, just to double check our work, okay, we're going to add up the mass. So 4 plus 55 is 59. Well, that adds up over here. 58 and 1 is 59. Adding up my atomic number, 2 plus 27 is 29. Again, looking over at the reactant side, 1 plus 28 is 29. So I've accounted for everything. In our last example, we're asked to fill in the missing information. So we see that we have technetium-98 being bombarded by a neutron to form a missing species and an alpha particle. So I'm going to start with what I know about a neutron bombardment as if I didn't have the alpha particle, and then I'm going to account for that. So I know in a typical neutron bombardment, my mass will increase by 1. So instead of having 98, I'll have 99. I know that my atomic number does not change because I'm not adding a proton, I'm adding a neutron. So if I hadn't also produced an alpha particle, this would be the identity of my species, atomic number 43. But it's not because I have an alpha particle. So let's remove that mass and remove those protons so we can find the identity of what's missing. So 99 minus 4 is 95. 43 minus 2 is 41. So this tells me atomic number 41 is niobium. Niobium 95 is our missing species. And we're just going to double check. So I'm going to just put this above. This is a bad space for it, but I'm going to put this above the question mark. Okay, so let's double check. Starting with 95 plus 4 is 99, and that's what we have on mass. 98 plus 1 is 99. Check. I've accounted for it. It matches. We're good. 43 plus 0 is 43. 2 plus 41 is also 43. So I've accounted for how these nuclei have changed.